Yeah, yeah, ready.
Great. How do you want to do the questions? Could people interrupt me, or you want to leave the questions for the end?
Maybe we can keep the question for the end. Yeah.
Sure. But both are okay. So if someone wants to
Okay.
ask questions whenever they want, please, if you have the option, feel free to do it.
Yeah.
Unmute yourself.
You can use the chat. You're seeing the chat, Alexandre? Or I can tell you.
It will be difficult to.
Okay. No problem. I can tell you if there's a question at some point.
Yes. So if there is something in the chat, feel free to stop me, unmute me, and ask it, and we can exchange.
Okay.
I like my talks to be very interactive and have the crowd interact and. So if let's try to do it also over Zoom if it's possible, or otherwise we can do it at the end. And thank you again, Jean-Bernard, for inviting me here. It's a great honor. Thank you for the long introduction. I apologize for the long biography. Today I want to talk about this famous buzzword, deep learning, AI for transportation. And I want to share all the things we have learned over the past 10 years now, almost all the trends and challenges that we did not expect initially and that we're trying to tackle now. I like to start my presentation with this quote. About 4 years ago, in fact, 5 years ago now, all governments, including the European Parliament, acknowledge that AI, artificial intelligence, will affect all segments of our society. 2 years later, they put mobility at the crossroads with a promise of having autonomous vehicle everywhere. Are we there yet? This is Switzerland today, and this is the future promised by AI. Autonomous vehicle in our daily life, such as self-driving cars, delivery robots, coexisting with us human in the open world. Optimism was and is still high. Yet I argue that the current state and even definition of AI might not be safe nor good enough to enable this feature. Let's look at the definition of AI. Any system that perceives its environment and takes action for its goal. So this is one definition coming from this reference. But naturally, many researchers over the past year or decades have used this definition to work on developing autonomous systems, autonomous vehicle, and they really try to focus on these two pillars, on perception and acting pillar. So naturally, the perception is in charge of understanding the current state of the world given sensors, and the acting pillar is in charge of planning the set of actions according to what we understand from the current state of the world. If you are aware of the trends in AI, you have heard about deep learning, and you know that we can do quite amazing classification tasks, such as detecting objects. And we now are able to use images and cameras to detect objects such as pedestrian and vehicle. Consequently, we start to see self-driving cars operating in highways or some streets in the US, in California, in Mountain View, based on deep learning. Yet, if you put them into my hometown and maybe in your own town over there, they fail to navigate this crowded scene where driving is based on social etiquette, where drivers telegraph their intentions. In these cities, when traffic is too dense, where bicycles are nearby vehicles, where the autonomous vehicle is basically surrounded by many traffic participants, it will suddenly stop and make other drivers even crash into it. There were a study in 2017 reporting that 98% of autonomous vehicle accidents are of this type, a sudden stop of the autonomous vehicle. It's not a perception problem. It's not the fact that the car was not able to detect something. It's actually the opposite. It was able to detect everything, but then it was conservative. It decided to stop, and it made other traffic humans participants to not be able to anticipate the behavior of the car and crash. So what was the problem? I claim that it's a lack of being able to predict what will happen next. It's a lack of forecasting capability. The autonomous vehicle, its AI, was not able to anticipate the behaviors of other traffic participants. Hence, I claim that AI cannot yet deal effectively with human free will. So let me introduce to you another type of autonomous vehicle, our little robot, Lumo, navigating alongside pedestrians in Lausanne. I argue that this is even harder than self-driving cars with respect to anticipating the future. Since the environment is not as structured as the highways and roads, and the dynamic of pedestrian has much more nonlinearity than vehicles. I claim that if we have the AI that can operate our robot in this environment, it can operate any autonomous vehicle. And indeed, when pedestrians are not in close proximity, AI is successful. Yet, it fails to navigate this crowded scene as it will freeze or lead to an accident, a collision. So to enable our robot navigate this crowd, AI must anticipate the social etiquettes, the unwritten social rules of navigation, such as respecting personal space, yielding right of way. And AI, again, must learn to deal with human free will. Let's look at a concrete example from our robot perspective. The perception pillar will detect and track these pedestrians. The acting pillar will output 3 paths that are physically possible and potentially select the shortest path. However, AI must understand that it is socially not accepted to navigate between these 2 people talking to each other, and it must forecast the behavior of the left person to not cross path. Hence, I claim that we need to introduce an additional fundamental pillar, a forecasting one. In fact, a social forecasting pillar in charge of predicting the future state of the world, predicting human-human interaction. For me, human-human interaction are referred to other type of moving participant. It can be other drivers, other bicycles, other pedestrians, other animals, any moving agent. So by combining perception and acting with our social forecasting pillar, it will pave the way to a new type of cognition I refer to as socially aware AI, AI augmented with social intelligence. Social intelligence is the ability to get along well with others and effectively negotiate complex social interactions. For us, social intelligence is the ability to forecast and anticipate the future, to predict all these interactions. If any transportation system is powered by such intelligence, it will have the capability to imitate humans and provide a sense of familiarity with the technology. Our autonomous vehicle will blend in and naturally interact with us humans in safe yet efficient manner. So now let me share with you what we have been doing with respect to each of these pillars, and I want to start with the new one that I'm proposing, the social forecasting pillar. We formulate the problem as given a sequence of perceived state, for instance, the coordinates of the agent. Let's predict the future state, the next 5 seconds. Our challenge is to model social interaction, is to model these dynamics that have correlation between the sequences and output a multimodal distribution because we have human free will. This formulation is also true for pedestrian. You can look at it as we want to predict the behaviors of pedestrian, we observe their state, their position, and we want to predict the next positions. They also face some social interactions and free will. For many years, the common practice was using knowledge-driven methods such as social force models. Social force model involves handcrafting some attractive and repulsive functions that are coming from our intuition of what is behind the causality of our dynamics. We can also use other mathematical frameworks, such as the discrete choice model framework complying with the random utility maximization theory. In 2016, when we saw the success of data-driven method for complex tasks such as image classification, speech recognition, and so on, we decided to naturally apply deep learning to solve the same problem. And we in fact were able to show that if we have enough data, we are able to outperform the knowledge-driven method with some standard metrics. And our first challenge was to model social interaction. So we have multiple sequences. How can we jointly predict multiple sequences that have some correlation? We proposed to model human social interaction as a binary occupancy map, a matrix X. And thanks to a neural network encoder, FE, for instance, we can map S to a compact latent vector referred to as a learned social representation. Then, given our learned latent representation, we can generate the prediction within our neural network. We studied different neural network architectures, functions, as well as new alternatives to our input space, such as using a tensor instead of a binary matrix, where each neighboring person is described with his own latent social representation. So nevertheless, the performance highly relies on carefully designing the loss function, our performance measurement. So this leads to our second challenge, outputting a multimodal distribution. Let's look at the two persons avoiding each other. The primary pedestrian on the left has the freedom to select 5 possible outputs based on her free will. If we train our network with an average L2 loss, which means minimizing the average behavior, we lose the 4 output modes. Y is the ground truth prediction, and Y hat is our estimates. If we train with the winner takes all loss, we lose the prediction accuracy. So you see all these blue lines that are outputting in all the modes. In 2018, we showed that we can train this architecture with an adversarial loss to improve the accuracy of the prediction. It's based on a min-max game between a discriminator trained to classify between a real and generated sample. So this is the famous GAN network, the generative adversarial network. And the quality of the prediction is much better, but we still suffer from mode collapse. We have then proposed a new paradigm to improve this mode collapse and the fact that we are missing some modalities in the probability, some behaviors, by rethinking how to use the generative adversarial network. We suggested that instead of throwing away the discriminator of GAN at test time, we use it to guide the sampling process again at test time. We can use its gradient to refine the samples that we are generating. By doing so, we are able to increase the prediction accuracy without losing mode. And this is illustrated in the last plot. Let's look at some quantitative results. I'm first reporting the average displacement error and the final displacement error of different methods. So when you do forecasting of a trajectory, you can compute these displacement error of your forecasted method with the ground truth. The smaller, the better. These numbers are in meter. What I want you to remember is the performance of the best knowledge-driven method, which is here, compared to the performance of data-driven methods. Here, we are sharing some of our own proposed data-driven method over the years. Let's take the best one, and you can see that we are doing better than knowledge-driven method. And in fact, the community has also proposed other data-driven method based on our findings, and they have also reached to very, very similar performance as our own data-driven method. So when you look at the average displacement error and the final displacement error, you're like, okay, data-driven methods are much better. Deep learning methods are much better than these knowledge-driven. However, transportation application is not only about the average behavior. It's crucial to study the worst case scenarios. It turns out that all these data-driven methods could potentially output unfeasible safety-critical solutions, leading to collisions. Hence, we decided to look at a new metric that is checking if the output is feasible and if the output is even dangerous. So we looked at the collision rate of these methods. And when you look at it, you see that knowledge-driven method, you can impose this knowledge that we cannot occupy the same space. You can hard code this and avoid it. So you could have a method that will lead to a zero collision rate. In our data-driven method, you're hoping that the deep learning architecture has learned that. But then when you look at the result, you see, no, we have a very high collision rate, which is quite surprising and in fact dangerous. So we have decided to shed light into the performance of this data-driven method, this deep learning method, with respect to this worst case analysis. And so how to do that? The motivation is naturally, okay, we have two worlds. We have knowledge-driven and data-driven. Can we get the best of both worlds? Can we use knowledge into our data-driven formulation? So we started to look at it, and we said that let's use the theory of discrete choice modeling to augment with data-driven formulations. So we can discretize the future step intention of pedestrian as illustrated in the bottom right of the slide, and each option has an associated hand-designed function utility, and an individual is assumed to select the option for which the utility is maximized. We can also rethink the output as a combination of a discrete high-level choice with continuous refinement. And the discrete choice is describing the high-level intentions, and the refinement can be described with a neural network that is looking at a residual to add to this high-level intention. And this residual can be looked as social conventions that we want to add to what we know from the physics. And we can view this formulation as disentangling the high-level coarse intent with low-level scene-specific nuances or culture-specific nuances of human motion. If you're interested into more details, you can look at this reference here, this recent publication, our CVPR work this year today, and that you will get much more details. This is what I wanted to talk about on our social forecasting problem. And I want to remind you the trends and the challenges that we need to face. When you do deep learning or machine learning, the first thing that you do is you collect a lot of data and you try to learn to imitate the data that you have. So in our case, we first thought that all we have to do is to collect as many trajectories as possible and train a network to minimize the error, for instance, reconstruction error in predicting these trajectories. But it turns out that this is not good enough. So first, when we were doing fully data-driven method for complex tasks such as image classification, it was very difficult for humans to describe why an image of a cat is a cat and not something else. But for mobility and navigation, I can describe why I am moving at a certain speed, I'm avoiding someone, why I'm actually navigating the way I am. So there are some knowledge, some information that I can share, that I can explain to someone how to move around. The same way that when I drive, I'm able to describe or to teach someone how to drive. You should follow the road, you should follow this speed. So there is a knowledge that is available that I can justify the output. I don't need to suppose that everything is coming from the data that I'm not able to explain. But there are a few based on social conventions, based on the way that we drive in Paris that is different from Italy, from UK, from China, from Iran, from South America, and so on. That is actually very useful to learn from the data, and I need to be able to disentangle these two things. The second is I was used again to look at metrics such as L2, reconstruction loss, like for regression task, but it turns out that in this type of application, I need to focus on metrics that are quite sensitive with respect to my goals, such as avoiding collision. So unfeasible output is very dangerous. It's much more dangerous to generate unfeasible output than minimizing the error. For instance, if I avoid someone, I want to avoid someone, and I decide to predict that I will avoid it from the left side as opposed to the right side, for instance, yielding left of way instead of right of way, this will generate a lot of error in my performance metric. So a safe choice is to predict that I'm going straight. I will lead to a collision, but I will still, I will minimize my error, my risk. But this going straight is extremely dangerous and wrong, and I should not even allow this. Finally, when I collect a lot of data and suppose that that's all I need, and randomly split my data into training, validation, and test set, what I might forget is that where is this data coming from? I should maybe not mix all the data so that I lose this knowledge that is coming from a culture, a social convention that is coming from a specific cities. So if I want to learn social convention, I should not mix all my cities together. I might need to learn from one city to learn what's specific to that city, and then study how to learn from other cities with much less example, how to generalize, and how to be able, again, to disentangle social convention with the physics. And these are the things that we have been working and we have been studying, is how to address all these limitations where initially we did not think of when we started to work on this application, and we discovered them over the recent years by trying to address all these performance challenges. If you don't have more questions, I'm going to continue to talk now about the other pillars and how you should rethink them, knowing that you want to predict also the future.
On your
Yes.
last point,
Yes.
I've seen that there's a kind of new challenge, the shift challenge, that has been proposed to cope with this kind of covariate shift problems that you had, that you train on some city and then you have to test on, and it's quite interesting. I haven't checked all the data set yet, but they have I think that they propose people to train on datasets from Russia, and then the test will be done on datasets from North America. So that could be interesting to see what we were just commenting about, how people I mean drive. Is dataset based mostly based on autonomous cars, I think, but probably there are pedestrians too. So it could be interesting to see just what you said here.
Absolutely. So in fact, again, when I say and when I share these limitation or things that we did wrong, it's really we, myself included, and the community, at least part of it. And indeed that we, when we collect this data set or even share it, we have a tendency to mix everything. So when you look at the existing vehicle data set from the companies, you don't see many work on transfer learning, on cross-domain and things like that. And we are now saying that, wait, we should do it actually. We should be careful. We should understand where the data is coming from and use it in the modeling to address this covariate shift and this issue of generalization and so on.
Right.
Yeah, and we have some ongoing work where we are doing it for all the vehicle data set. We are trying to now index them according to the cities and also for the pedestrian. We had this Trajan plus data set where we mixed everything, and now we're saying, oh no, maybe we should provide also from which location and city the trajectory is coming from, so that we can better address these issues.
Okay, so you will modify Trajan plus to include this kind of information?
We now realize that we should.
Right, yeah.
Initially, we thought that no, let's take all the data set and mix, and now we're like, wait, but if we do that, how can we claim that we learn social convention? Because they're not the same, so it's not normal to suppose. Yeah.
Hello, I have another question. I believe, well, it's kind of the same as Jean-Bernard said, but for example, do you consider also not only the people, but also the environment? Like, for example, in Europe, for example, in Amsterdam, there are many bicycles, many trams, or in many cities in Europe, that's really common. But in America, it's not quite common. So I don't know if you consider that as well.
Absolutely. So when we started this trajectory forecasting, we first focused on only pedestrian interactions, only humans, so that we wanted to make sure that we can learn the basic avoidance and things like that. But now, if you really want to solve this, you need to take care of all the other agents, like in their type of dynamics. So it can be a bicycle, it can be a vehicle, it can be a scooter. So we have different type of constraint on the dynamics, so we should model that. And when it's a vehicle, even a pedestrian, the static scene has an influence, especially if you know that there are doors, attractors, there are many things that attract your dynamic, or and also the static environment needs to be modeled. So when you do, for instance, vehicle trajectory forecasting, the static is extremely relevant, obviously, and you try to come up with nice ways to encode the environment as well as the dynamic.
Okay, so the second question is, mix all the environment that you mentioned before.
Yes.
It's not kind of inefficient right now. I mean, you can optimize depending of the data set or depending on the location in some way to get a smaller data set, but also consider the risk that if you have a similar behavior for some reason, even if it's an statistical error, I would say, you have a bicycle where it's supposed to don't be, for example, a bicycle rider. You can potentially cause an accident because you didn't consider the full data set, right?
So I don't know if I understand your question correctly, but maybe let me frame it in a way that, and you can tell me if this is where you're going. It's true that we will not be able to collect data from everywhere and to potentially be able to learn for each city how to behave, right?
Yeah.
So what we think, what we want to be able to do is, for instance, we humans, when we go to a new city, we have never actually observed dynamics from there. So in the beginning, we are very conservative, we're not so good, but then we learn very quickly and can adapt and navigate the same way. But we have at least the skills to navigate in a very conservative way that might not be as efficient as the others, but it's still safe. And okay. I think this is coming from our understanding of the physics, not the social convention. So what we want to do is to develop algorithms that will understand the basics and then learn the social convention with very limited number of examples. And we want to be able to show that if you go in a new environment, you will do okay, but if you actually adapt the model with few examples, you will do as good as the others.
Okay, got it. Thank you.
That's what we want to try to prove, and we haven't yet. But
okay, thank you.
Cool. Any other questions on this topic? So if not, I'm gonna continue to talk about perception. It will be a bit faster. So perception is a computer vision problem. So given an image, you want to detect and understand everything. What we thought for many years is that if I can put a bounding box and locate humans, that's all I need to be able to have a car or a vehicle or a robot to navigate the space. I mean, as long as I can detect, this is all good enough. And this is the challenge. So let's add sensors, LiDARs to solve this problem, because this is the key. But now that I've tried to convince you that that's not good enough to predict, we want to predict the future. So if I want to predict the future, putting a bounding box might not be good enough. And what we are promoting is, let's detect much more. So let's detect, for instance, the human body pose, the skeleton. And I like to look at it as semantic key point. All these points have a semantic meaning. So I want to detect the left shoulder, the right shoulder, and so on. And then I can also extract other attributes on humans, like what are they doing, their activities. I can understand, obviously, the 3D, but also relationship and so on. What is quite common is that let's first do detection. And here we have shown that when you want to detect and understand the 3D, you can even do it with a single camera and extract depth information from a single camera and locate these humans in 3D. But what is really interesting in transportation, again, is that in this type of application, computer vision for transportation, you need to deal with challenges that might not be true in other applications. And for instance, you have to deal with limited resolution and with partial information. The object that you're looking at, even you have beautiful cameras, beautiful HD, 4K, at one point they will be far, they will have limited pixel on them, and they will be occluded with other things. So you need to be able to detect them. You need.
I have
yes.
Another question regarding that. Do we know what is the limit of number of people we can detect or number of objects we can track in real time?
There is no limit. There is no limit. So it depends on the algorithm, but here you have actually this demo online. You can click on Vita demo. You can detect as many humans as is visible, and the cost, computational cost, is not a function of the number of humans.
Okay.
Same here. So this demo that you see, the videos that you see, it's real time because we have what we call a bottom-up method. The input is an image, and it puts a point on all the humans. So regardless of if they're one or two, it's the same cost.
Okay. So it could be super crowded and it won't be any different then?
No difference on computational cost.
Okay.
But this is related to your algorithm. So there are algorithms that are top down, and this will be related to the number of humans. But if you have bottom-up algorithms, it's not. And that's what we are promoting, bottom-up.
Okay. Thank you.
And then the other requirement is that because, as mentioned, we want to do many things. So you want to extract, you want to solve many tasks. And for each of these tasks, you might not have enough example, but you still want to do them. So it's a very interesting multitask formulation. So what we are studying is, can we have a method that will take a single image as input, learn a representation that is good enough for many tasks that can do pose, activities, detection, and so on. And for instance, here you want to do detection, but also tracking across time. So we have shown that we can jointly detect this key point in time and in the spatial domain. So over the image and also across time. And we can also extract all these attributes in real time in the same formulation. So you have an image, the output is all this information on every humans. So like the fact that there is a human, it's an adult, it's the person is looking to the camera, has a stroller cart, and we can even estimate their intention of crossing the road or not. Here is an illustration of that. We draw in blue pedestrian where the algorithm thinks that they will cross the road, and in green the ones that they will not. And this is also very useful to better anticipate and plan the dynamics of the car, and to have a behavior that is not too conservative, but is matching human behavior.
Can I ask
yes,
something?
Yes.
On this example, I guess that you probably have also another task for segmentation or something like that to understand, I mean, to translate the notion of crossing into.
No, so
passing
We
from
jointly do, in fact, here, body pose detection and intention estimation.
Okay. Okay.
So you see in the bottom, so we have the image, we ask the network to tell us where the body pose, and we also ask the network to draw the pixel that correspond to someone that will do the crossing or not.
Okay. Okay. Without needing to also try to see where the street is.
No,
the
no,
is,
we suppose that the network is learning this from the data.
Yeah.
But
exactly.
we don't explicitly model it here.
Okay.
Yes, and you can have more detail in this reference. This is another illustration where we do semantic key point extraction on Vehicule. And as I mentioned, a lot of previous work just put a cuboid on humans or on Vehicule. And we believe that we should put this skeleton on these objects to better predict what they will do next and understand their state and so on. And we are showing here that this is possible. So we can really detect all these traffic participants with that level, that much details.
Just as a comment, in Guanajuato, that could be cool to have.
Sorry?
Something in Guanajuato here, in the city of Guanajuato, it could be cool to have something like that for cows. Because we have, well, there's kind of problem.
We are doing it.
Urban planning problem with cows wandering in all the city and causing some problems with cars.
Yeah, so this this algorithm to extract the body pose. We also have a version for animals, and it was for this application. Like we say, in urban environment, you have dogs, you have cows, you have horses. We never know. I mean, you still want to also detect them and understand their state. Right. So here to sum up our perception work. Basically, what we are trying to advocate is that we should not suppose that putting a bounding box on humans is all we need, and understanding the current state and no attributes, that's good enough. We claim that we need to have a very detailed understanding of the agent, such as understanding the body pose, understanding their state attributes. Is it a kid? Is it an adult? Understanding potentially their intentions so that we can better do prediction and then planning. All these perception algorithms are available as a live demo here. You can select the algorithm of this key point detector and you can run them in your browser. It's super fun. Now on the acting pillar, previous work have shown the power of modeling human-robot interaction within the reinforcement learning framework. We have shown the power of also modeling human-human interaction within the same framework. However, our learning is quite sample inefficient and did not generalize well to all the crowded scene. Hence, we're currently working on learning a shared representation again that is able to do forecasting and planning. And we want to improve all the challenges related to reinforcement learning that are due to simulation bias and so on. Maybe this is close to the end. I want to also share what we have been doing on the teaching side. Teaching deep learning for autonomous vehicle. And as a class project, we asked the student to develop the algorithms to be able to do a race with these robots. So we have all these Lumo, all these robots that are supposed to track something, the student, and then they need to race on a track to arrive first. So each team is made of a robot and a student, that run into a track, and they will need to basically avoid each other, follow each other, and be able to arrive first into this competition. This was very, very fun. It was, to the best of our knowledge, the first worldwide human-robot tandem race. And it was extremely fun to see the students succeeding in doing this. I'm gonna basically end my presentation by saying that these three pillars can be applied to much more than autonomous vehicle. It can be applied to any intelligent system. For instance, you can even apply it to control traffic light at the city scale. You can have security or traffic cameras or drones that will be able to understand traffic, at the city scale. They will be able, and then you will be able to predict maybe where these cars will go, the origin and destination of all the traffic. And according to that, better control the traffic lights so that you can reduce congestion, you can reduce, obviously, pollution, and have a much more sustainable city. I'm gonna end here. I'm hoping that I've convinced you that there's a bit room, but we still want to make this bright future a reality, and it's possible. Everything that we do publish is open science. We share the code. You can use any of the code that is available that we put online. And I also want to obviously thank all the PhD, postdoc, our sponsor, who are behind all this work. I'm happy to take your questions.
Thank you very much. To the audience, feel free to ask anything.
I have a question about how the robots make decisions. I wonder if they model themselves as a pedestrian, and by that they make a prediction, and therefore they act upon that prediction, or do they have a different model for decision making?
This is a very good question, in the sense that you can do both. So when we try to learn to predict, which is our basically social forecasting pillar. So if we have the forecasting model, we can then use it as is, and supposing that the robot is one of the pedestrians, right? And suppose that we humans will behave the same way around the robot as if it was a pedestrian. Or we can say, no, humans behave differently around the robot, and the robot has also, has his own policy, and let's minimize a reward for the robot that is based on efficiency, shortest path, and energy, and let the robot has this type of his own policy based on the reward that we define. And this is what people have done with reinforcement learning. So they define their own reward function and let the robot decide of a policy that might not match humans. And we are looking at both paradigm, and what I suspect is that maybe the most optimal paradigm is what we humans are doing. But I don't know, this is a philosophical question. So when you look at bio-inspired and what we humans are doing, we realize how efficient and beautiful it is. So it will be very interesting to show that by defining some relevant reward function, the optimal solution is what we humans are actually doing. So that is a very cool philosophical study. That was a long answer to your question. I don't know if it was clear.
Yeah, but I think it answers. Thank you. And thank you for the presentation.
Thank you.
More questions? Just out of curiosity, the project that you saw, that you showed from your teaching, is at which level?
Master, yes.
Level? Master level, okay. And it's 6 months?
No, they did this
in
few weeks, 2 months.
Okay.
As part of,
Okay.
so they had 4 hours per week. So, but we gave them a lot.
Okay.
So what they had to do is to develop only the detection algorithm.
Yeah.
So we give them the framework, the code, and in fact, this is also available, I think, online somewhere. So if someone wants to reproduce this type of challenge with this type of robot,
it's within ROS,
sorry?
I guess. It's within ROS, the framework?
ROS, absolutely.
Okay.
Someone is asking for the demo. I think there was a mistake in the link. Yes, I'm going to put back the link so that they can better copy paste it. And yes, there was a typo. There is no edu in the link that they put in the chat. So just to disclose how the demo works, it's one desktop with one GPU. So if everybody connects, very likely it will be very slow or it will crash. I don't know, but and we take the images from your camera, send it to our computer in Switzerland, do the algorithms, and then send back the results. So the delay is due to the communication also. And you can select the webcam, you can upload an image, a video, you can set the algorithms. I don't know if it's working for someone.
Yeah, it is working now.
So if you select, for instance, the whole body accurate, you will see 100 key points on humans. So on the face, on the hand, we're taking all these things. It's our ICCV paper that will be presented this week. And it also works with animals. If you go outside with your iPhone, you can use it, test it, or Google phone or any phone, smartphone.
Okay.
There's a question in the chat by Nuba. If you can identify the social context as person A being merged by persons B and C, should the robot drive over B and C?
So I mean, this is a similar question as all these ethical dilemma, right? So yeah, we also have other research on this, and this is an illustration. What should the robot do if there is it's facing ethical choice? And this will be, I guess, for a longer presentation. I sometimes talk 2 hours about this topic, and indeed, even in the class that we teach, we have a full session on the role of ethics in implementing this autonomous vehicle. And we should all researchers be aware of that and think of what does it mean, what we should be careful, what we should also consider in implementing this, how we can get help, and who can suggest some implementation design, and so on. And it's a very sensitive topic. A lot of so the way this goes, I make a survey from the crowd, and then you realize that nobody agrees. There's no universal ethic, and then there is a lot of emotional answer. We brainstorm. Initially, there is a bit of 50-50 vote on the two options, and then after discussing all the pros and cons. People are convinced about one option and we get about 80-20, but there's still 20% of people that will disagree regardless of all the rational arguments. And that's true also in reality. But in governments and other policymakers have made the decisions of what's correct and what's not. Either you apply that or you enter an autonomous system and you share your own ethics. You say, okay, we're going to ask you a set of questions or put your, what is your ethic, and let the system then make the same decision as you in this sensitive decision. These are the things that we are studying now.
Talking about ethics, how can we complain with this kind of mechanism with the, for example, the GDPR that here in Europe or in all the world, or all the privacy conventions that we are implementing now? How can we make sure that we comply with all them?
So privacy is a bit, to me, it's one component of the ethics, and there are a lot of ways to deal with it. Collecting data that you have human agreement, or not saving images, just running your algorithm in real time. So extracting, for instance, skeleton without keeping any images, so you protect human privacy. So, or it's always a matter of a reward and what you get by giving a bit of your privacy with respect to every application, even in the medical domain. So this is, I think, something that we have came up with a lot of solutions. So I don't think this is a bottleneck.
Okay.
We need to respect it. We need to absolutely be careful and make sure that we're also respecting the privacy component of what we do. But there are a lot of mechanisms to do that.
More questions? No? Okay. I think that no more questions. So, well, again, thank you very much for your time, Alexandre.
Thank you for the invitation.
Nice talk. Yeah, I hope that maybe when times become more quiet and then when we get rid of the pandemics and so on, we could invite you over. I think that you could see other context, social context.
Yeah, absolutely.
Yeah.
Fantastic.
Yeah. Okay. So thank you very much. Thank you.
Bon appétit, provecho, I think, right? In Spanish, no?
Buen provecho.
Bon provecho.
Sí. Buen provecho.
Have a good lunch.
Thank you very much.
Thank you. Bye-bye.
Bye. Bon appétit.
Yeah.
Bye.
Bye.